April 1945. The war is dying but not yet dead. A German engineer stands in silence inside a factory in Detroit, his uniform stripped of insignia, his hands empty of tools. He was brought here for interrogation. What they expected was propaganda. What they found was something else entirely. The assembly line stretches beyond sight. Machines roar in perfect rhythm. Welders throw sparks like constellations. Tank hulls move past him every 3 minutes, complete, painted, ready for war. The noise is deafening, relentless, inhuman. He watches American workers, young, old women in coveralls, move with practiced efficiency. No craftsmen here, no master artisans, just system, just speed. Just an endless river of steel. The machines never sleep, and neither did the men who built them. He whispers to another prisoner beside him, barely audible over the thunder of industry. We could never have done this. Not with pride, not with defiance, with awe. In the 1930 seconds, Germany believed itself the pinnacle of human engineering. Precision instruments, advanced optics, chemical mastery, automotive excellence. The world looked to Berlin, to Munich, to Stuttgart, and saw the future rendered in chrome and blueprint. German officers spoke of American industry with barely concealed contempt. A nation of mechanical amateurs, they said. A country that valued quantity over quality, speed over craftsmanship. Where Germany built instruments of war with the care of watchmakers, America churned out refrigerators and radios for the masses. Where German tanks were engineered masterpieces, American vehicles were crude, simple, utilitarian. They built precision. The Americans built quantity. But as the war unfolded across 2 oceans and 3 continents, something unexpected happened. Quantity became a new kind of quality. Volume became virtue. Speed became strategy. How did the land of assembly lines, refrigerators, and Hollywood suddenly redefine modern warfare? In 1939, German panzers swept through Poland in weeks. The Blitzkrieg was not just a tactic, it was proof of concept. Superior engineering, superior training, superior vision. By 1940, France had fallen. By 1941, Germany stood at the gates of Moscow. The Wehrmacht seemed unstoppable, inevitable, destined. Then, America entered the war. Within 3 years, American factories were producing a plane every 5 minutes, a tank every 7 minutes, a ship every 4 days. Numbers that German intelligence officers dismissed as Allied propaganda, impossible exaggerations meant to demoralize the Reich. But they were real. The war that began with German efficiency would end with American automation. The conflict that opened with precision strikes and calculated maneuvers would close with industrial arithmetic, a mathematics of production so overwhelming it rewrote the rules of modern conflict. Berlin had designed war as an art form. Detroit redesigned it as a science. Fade from the drawing boards of German engineering firms to the thundering heart of American steel mills. From the myth of craftsmanship precise and proud to the reality of mass production relentless and unapologetic. From workshops where masters trained apprentices in generations-old techniques to factories where 18-year-old women operated machines that could outproduce an entire German facility. This is the story of how technology became something more than genius, how it became system. When Henry Ford's engineers first looked at the blueprints for the B-24 Liberator bomber, they saw an impossible puzzle. 4 engines, thousands of rivets, complex hydraulics. A flying machine that required precision assembly by skilled aircraft workers. The kind of thing built slowly, carefully, one at a time. Ford saw something else. He saw a car with wings. Willow Run rose from Michigan farmland like a cathedral of industry. 1 building, 1 mile long, the largest room under a single roof anywhere on Earth. Inside, the assembly line moved constantly, pulling partially completed bombers through stations where workers added pieces, systems, instruments, each person performing one task, repeated endlessly, perfected through repetition. The first B-24 took months to complete, engineers argued. Systems failed. The complexity seemed to mock Ford's vision of mass production applied to aircraft. But Ford's men were patient. They broke down every process, simplified every connection, standardized every part. What took skilled craftsmen hours they reduced to minutes. What required judgment they reduced to procedure. By 1944, Willow Run was producing 1 complete B-24 Liberator every 63 minutes. 63 minutes. From bare frame to fully operational 4-engine bomber capable of carrying an 8,000-pound bomb load across a continent, German intelligence officers read the reports and dismissed them as fantasy, propaganda designed to create false impressions of American capacity. The mathematics made no sense. A bomber every hour impossible. Their own factories, staffed by skilled workers using precision tools, could produce perhaps 1 aircraft per day if everything went perfectly. But the photographs kept coming. Reconnaissance flights over American industrial centers revealed the truth. Airfields packed with new aircraft, parking lots filled with thousands of bombers waiting for crews. Production that defied every assumption about manufacturing capacity. To the Reich, precision was honor. Mass production was vulgar. But vulgar or not, it was real. German airmen began to notice it first. Over France, over Germany itself, the sky grew thick with American planes. Lose 10 bombers in a raid. 20 more appeared the next day. Shoot down a squadron. 2 squadrons replaced them within a week. They thought they were fighting men, skilled pilots, brave crews. Individual warriors whose loss mattered, whose replacement took time. They were wrong. They were fighting machines that made more machines. Factories that produced not just bombers, but the capacity to produce more bombers. A system that fed itself, that grew stronger through its own momentum. A Luftwaffe pilot captured in late 1944 sat in an interrogation room and spoke quietly about what he'd seen. Not about tactics or targets, about numbers. About the impossible endless wave of American aircraft that filled European skies like a metal storm. We could shoot them down, he said. We did shoot them down. But they kept coming. More, every day. We realized eventually we weren't fighting a country. We were fighting an industry. The assembly line had gone to war, and war would never be the same. In Berlin, German engineers studied captured American aircraft, looking for the secret. Better alloys, more powerful engines, some revolutionary technique. What they found was simpler and more devastating. Standardized parts, simplified assembly. Processes designed not for perfection but for speed, not for beauty but for quantity. The Americans had turned war into manufacturing, and manufacturing they had already mastered. The mathematics of war changed in 1942. It became arithmetic, cold, simple, overwhelming. Germany's factories hummed with activity. Skilled workers bent over lathes, crafting components with micrometer precision. Engineers inspected each aircraft, each tank, each weapon system with meticulous care. Quality control meant something in the Reich. Every machine that left a German factory was tested, refined, perfected. In 1943, Germany produced roughly 25,000 aircraft, an impressive number by any historical standard. More than they'd built in 1942. More than seemed possible given the Allied bombing campaigns that were beginning to tear at German infrastructure. America produced 96,000 aircraft that same year. 96,000. Not as an absolute maximum, not pushing capacity to breaking. That was simply the output of a system running efficiently, steadily, without particular strain. The numbers existed in different universes. German factories depended on skilled craftsmen, men who'd spent years learning their trade, who understood the intricacies of aircraft construction, who could identify problems by sound or feel. Lose those men to conscription or bombing and production suffered. Training replacements took months or years. American plants ran 24 hours a day using semi-skilled labor. Workers learned single tasks in days or weeks. Standardized parts meant anyone could assemble components following simple instructions. One shift ended, another began. The machines never cooled. The assembly lines never stopped. A German aircraft might be superior in specific ways. Better climb rate, tighter turning radius, more elegant engineering solutions to complex problems. But for every German fighter that took to the air, 5 American fighters were already waiting. Tanks told the same story. Germany's Panthers and Tigers were technological marvels. Thick armor, powerful guns, sophisticated engineering. Each one took thousands of man-hours to produce. Each one represented the peak of German armored vehicle design. America built Sherman tanks the way it built cars. Welded hulls, cast turrets, engines borrowed from existing designs. Nothing revolutionary. Nothing particularly impressive to an engineer's eye. But they rolled off assembly lines in numbers that made individual superiority irrelevant. By 1944, America was producing more war materiel than Germany, Italy, and Japan combined. Not slightly more, overwhelmingly more. A production advantage so vast it rendered tactical brilliance nearly meaningless. German generals who'd studied Clausewitz and Napoleon found themselves fighting something those strategists never imagined, an enemy whose strength grew faster than it could be depleted. Destroy an American armored division, and two more appeared. Sink a convoy, and larger convoys sailed the next month. The Eastern Front devoured German resources. The Western Front demanded more. Italian facilities collapsed. Japanese industry operated on a fraction of the scale needed. And still American production climbed. A German officer interviewed after the war spoke with something like sadness in his voice. Our machines were beautiful, he said. Precision instruments, works of engineering art. But theirs were infinite. Infinite. The word kept appearing in German assessments. Endless production. Inexhaustible reserves. An industrial capacity that seemed limited only by the physical constraints of geography and time. Berlin planners had calculated based on traditional assumptions. Industrial capacity could be bombed. Supply lines could be cut. Economic strain would eventually limit production. Every previous war had followed these rules. But America wasn't following the rules. America was rewriting them. The numbers war had begun, and Germany, for all its engineering genius and tactical innovation, was losing to mathematics it couldn't counter. Addition and multiplication, simple arithmetic, applied with relentless mechanical precision. Sometimes revolution arrives not in complexity, but in simplicity so profound it seems almost insulting. The Jeep was never meant to be remarkable. No engineer looked at its design and saw beauty. No general examined its specifications and felt awe. It was a quarter-ton reconnaissance vehicle, built to an impossible deadline. The army wanted prototypes in 49 days, production models in 75. What emerged was utilitarian to the point of brutality. A steel frame, 4 wheels, an engine barely powerful enough for its purpose. No doors, no roof, seats that offered comfort as an afterthought. It looked like something sketched on a napkin and rushed into production before anyone could overthink it. And it was perfect. 600,000 Jeeps rolled out of American factories before the war ended. They appeared on every front, in every theater, under every condition imaginable. Desert heat, Arctic cold, Pacific jungles, European mud. The Jeep didn't care. It ran. Brake an axle. Replace it in 20 minutes with standard tools. Engine trouble. Swap it out in an afternoon. Parts were interchangeable. Repairs were simple. Any mechanic with basic training could keep a Jeep running indefinitely. Germany had equivalent vehicles. The Kübelwagen was lighter, more fuel-efficient, cleverly designed. But it was complex. Specialized parts. Careful maintenance requirements. In ideal conditions, it performed admirably. In the chaos of actual warfare, it became a liability. The Jeep thrived on chaos. It was designed for a world where things broke, where conditions were terrible, where elegance mattered less than function. American engineers had built it assuming worst-case scenarios, and those scenarios became reality across every battlefield. Soviet officers loved the Jeep. British commanders requisitioned them eagerly. Even German soldiers, when they captured one intact, kept it running and used it until ammunition ran out. It became a universal vehicle, transcending national boundaries through sheer practical utility. A German engineer, part of the post-war technical evaluation teams, spent weeks examining captured American equipment. He documented everything meticulously: specifications, materials, manufacturing techniques. His report on the Jeep was brief and tinged with something like reluctant admiration. It represents a philosophy we never understood, he wrote. We built vehicles to perform optimally under specific conditions. They built a vehicle to perform adequately under all conditions. We pursued perfection. They pursued reliability. In war, reliability won. The Jeep wasn't elegant. It wasn't sophisticated. It didn't represent any particular breakthrough in automotive engineering. But it was everywhere. And everywhere beat better when everywhere meant every beach, every mountain pass, every improvised road carved through wilderness. American soldiers modified them endlessly. Mounted machine guns, added armor plates, stripped them down for speed, loaded them beyond capacity. The Jeep absorbed abuse and continued functioning. It became not just a vehicle, but a symbol of American pragmatism, of industrial democracy, of the idea that good enough produced in massive quantities trumped perfect produced in limited numbers. 600,000 Jeeps, each one simple enough that a farm boy from Kansas could maintain it. Each one cheap enough that losing one didn't matter strategically. Each one reliable enough that commanders planned operations assuming they'd work. Captured German engineers studied them with fascination. Not the fascination of discovering something revolutionary, the fascination of recognizing something obvious they'd somehow missed. War didn't reward the most elegant solution. It rewarded the solution that worked when everything else failed. It was not built for perfection, one engineer noted in his journal. It was built to win. Simple words, devastating implications. While armies clashed with steel and fire, another war unfolded in the invisible spectrum, a conflict fought with electromagnetic waves and mathematical logic, where victory belonged not to the strongest, but to those who could see furthest, into the dark. Germany had radar. They developed it independently, deployed it defensively, understood its potential. German scientists were not ignorant of electronic warfare. Their research was solid, their equipment functional, their theory sound. But America had something else. America had industrialized electronics the same way it had industrialized everything else, not as individual innovations, but as mass-produced systems, standardized and replicated across thousands of installations. By 1943, American radar networks stretched across coastlines and battle zones like invisible webs. Ships carried radar, aircraft carried radar. Even some artillery shells carried miniaturized proximity, fuzzies, tiny radar systems that detonated explosives at optimal distance from targets without requiring direct hits. The proximity fuse was witchcraft to those who first encountered it. Anti-aircraft shells that exploded near aircraft without contact. Artillery that detonated above enemy positions at precisely calculated heights. How could a shell know where to explode? German intelligence recovered unexploded rounds, dissected them carefully, found the secret vacuum tubes, capacitors, miniature radar transceivers, all packaged inside an artillery shell designed to survive the violent acceleration of being fired from a cannon. The engineering was extraordinary. The manufacturing was impossible, except America was producing them by the millions. Each proximity fuse required precise assembly, careful calibration components manufactured to tight tolerances. The kind of device that should have been produced in small numbers by specialists. Instead, they came off assembly lines in quantities that transformed anti-aircraft warfare from an art of prediction into a science of certainty. Luftwaffe pilots began dying from unseen guns. Shells exploded around them without warning, without apparent cause. The mathematics of aerial combat changed. Flying at night no longer provided safety. Radar could track you. Flying low no longer helped proximity. Foes' artillery could catch you there too. The illusion of German technological superiority fractured against this electronic reality. In England at Bletchley Park, another kind of technological leap was occurring. The British had broken German codes, but breaking codes manually took time, sometimes days, to decrypt a single message. Information arrived too late to be useful. American and British engineers built machines to accelerate the process. Not calculators, not simple aids. Actual computing devices, electronic brains that could test thousands of code combinations per second. ENIAC, the electronic numerical integrator and computer, emerged from this need. 18,000 vacuum tubes, 30 tons of equipment, 5 million hand-soldered connections. It could perform 5,000 additions per second. A number that meant nothing to generals, but everything to mathematicians, who understood what computation at that speed implied. Germany had brilliant cryptographers. They had mathematicians who understood information theory. They had scientists who grasped the potential of electronic calculation. But they were working individually in scattered facilities without the industrial infrastructure to transform theory into mass application. The Americans were not just building better electronics. They were thinking differently about what electronics could become. Not instruments to be perfected, but systems to be deployed. Not individual breakthroughs, but networked capabilities. When German engineers examined captured American radar equipment after the war, they found nothing revolutionary in the basic technology. What shocked them was the scale. Thousands of identical units, standardized components, training programs that taught operators to use equipment in weeks rather than months. "We were building instruments," one German radar specialist admitted. "They were building infrastructure. The invisible war ended the same way the visible one did. Not with a single innovation, but with systematic application of technology at a scale Germany couldn't match." The Atlantic Ocean became a graveyard. German U-boats prowled the shipping lanes like wolves, and the mathematics were brutally simple. If Germany could sink merchant ships faster than the Allies could build them, Britain would starve, and the war would end without a single German soldier setting foot on English soil. In 1942, the equation favored Germany. U-boats sent millions of tons of Allied shipping to the bottom. Convoys sailed into the Atlantic and vanished. Supplies destined for Britain never arrived. The Battle of the Atlantic was a war of arithmetic, and Germany was winning. Then Henry Kaiser changed the equation. Kaiser was not a shipbuilder. He'd made his fortune building dams and roads, pouring concrete across the American West. He knew nothing about naval architecture or maritime tradition. He knew construction, and he knew speed. Traditional shipbuilding was craftsmanship. Skilled workers riveted steel plates one at a time, fitted components with careful precision, built vessels that would last decades. A merchant ship took months to construct, sometimes a year. Each one was unique, individually crafted, a floating testimony to the builder's skill. Kaiser looked at that process and saw inefficiency. He saw construction, not craftsmanship. His shipyards on the west coast became assembly lines for the sea. Hulls were welded, not riveted, faster, stronger, requiring less skill. Ships were built in sections prefabricated like pieces of a giant puzzle, then brought together and joined. Workers specialized in single tasks, repeated endlessly. One team welded hull plates, another installed engines, another fitted electrical systems. The first Liberty ship took 244 days to complete. Engineers worked out problems. Processes improved. Techniques evolved. 4 months later, Kaiser's yards were launching a new Liberty ship every 4 days. 4 days. From keel laying to a fully operational merchant vessel capable of carrying 10,000 tons of cargo across an ocean. The Robert E. Peary, built as a demonstration of peak efficiency, went from start to finish in 4 days and 15 hours. Photographers documented every stage. Newsreels carried the footage. The world watched disbelieving. German U-boat commanders noticed the change. They were sinking ships, more ships than ever. Their tactics were working. Their torpedoes found targets. But the convoys kept growing. More ships appeared than disappeared. The arithmetic reversed. In 1943, Allied shipyards launched 3 new merchant vessels for every one the U-boats sank. The industrial advantage was so overwhelming that Germany's tactical superiority became meaningless. Sink a convoy today and 2 convoys sailed tomorrow. Liberty ships were not elegant. Maritime professionals looked at them with barely concealed disdain. Welded hulls were crude compared to riveted construction. Standardized designs lacked the character of traditional vessels. Some cracked in cold water, some broke apart in heavy seas. They were industrial products, not ships in the romantic sense. But there were 2,700 of them. 2,700 Liberty ships launched between 1,941 and 1,945. An armada built not by shipwrights, but by a construction magnate, applying assembly line principles to the sea. A German admiral interviewed after the war spoke with weary resignation. "We sank ships," he said. "We sank many ships. Our submarines were effective, our commanders skilled, our tactics sound, but we could not sink their factories." The Battle of the Atlantic ended not with a naval engagement, but with industrial exhaustion. Germany couldn't build U-boats fast enough, couldn't train crews fast enough, couldn't maintain the pressure against an enemy whose merchant fleet grew despite losses. Kaiser had won a war of arithmetic with multiplication. Simple, brutal, effective. The ocean remained a graveyard. But now the graves were empty, and the ships sailed on. The B-17 Flying Fortress became the symbol of American air power, not because it was the best bomber ever built, but because there were so many of them that individual superiority stopped mattering. 12,700 B-17 seconds rolled out of American factories during the war years. They filled the skies over Europe in formations so large they looked like migrating flocks of steel birds. German fighter pilots attacked them with courage that bordered on desperation, knowing that shooting down one bomber meant nothing when 50 more flew behind it. The B-17 was tough. It could absorb punishment that would destroy lesser aircraft. Pilots brought them home with engines missing, with holes torn through wings, with tail sections barely attached. The bomber became legendary, not for its perfection, but for its resilience, the ability to take damage and keep flying. But the B-17 was conventional. Advanced for its time, certainly, but built using known principles, established engineering, familiar technology. The B-29 Superfortress was something else entirely. It cost $3 billion to develop and produce, more than the Manhattan Project, more than any single weapons program in human history. It was a bet that technology could leap forward, not incrementally but dramatically, that American industry could build something that existed beyond current capabilities. Pressurized cabin, remote-controlled gun turrets, engines more powerful than anything previously mounted on an aircraft, range sufficient to fly from island bases to Japan and back, bomb capacity measured in tons, not pounds. The B-29 was not an evolution. It was a revolution wrapped in aluminum and ambition. Engineering challenges emerged constantly. Engines overheated. Systems failed. Test flights ended in crashes. The aircraft pushed every boundary simultaneously: weight, speed, altitude, range, payload. Each problem solved revealed three more. But American industry absorbed the problems and solved them through sheer industrial determination. More prototypes, more tests, more refinements. Money flowed, resources appeared. The project never slowed because stopping was unthinkable. When the first B-29 seconds appeared over Japan in 1944, Japanese defenders struggled to reach them. The bombers flew at altitudes where interceptors lost performance, where anti-aircraft fire couldn't reach effectively. They struck with impunity, then vanished into the distance. German officers examining B-29 wreckage after the war, some had been damaged over Japan, and studied by German advisors, stood in silence before the technological leap it represented. The pressurization system alone was beyond anything in German aircraft. The fire control computers that aimed the remote turrets were electronics Germany hadn't even conceptualized. The engines represented metallurgy and design years ahead of current German development. One Luftwaffe engineer, a man who'd worked on Germany's most advanced aircraft projects, examined a B-29's central fire control system, the analog computer that coordinated all defensive guns, calculating lead elevation and azimuth automatically. He ran his hands over the mechanisms with something approaching reverence. It was as if it came from another century, he said later. Not the next decade, not 5 years ahead. Another century. The B-29 was not just an aircraft. It was a statement, a demonstration that American industry could take on challenges considered impossible and systematically solve them through organization, funding, and relentless engineering. Germany had produced remarkable aircraft. The Me-262 jet fighter, the V-2 rocket. Individual breakthroughs that showed German innovation remained formidable, but they were individual breakthroughs, produced in small numbers, limited by resources, by time, by the fragmenting chaos of a collapsing empire. The B-29 was produced by a nation at the height of its industrial power, throwing resources at a problem until the problem ceased to exist. 3,900 B-29 seconds were built before the war ended, 3,900 aircraft from the future. In the New Mexico desert in Tennessee, valleys in Washington state, in laboratories scattered across a continent, 130,000 people worked on a project most of them didn't understand. They processed materials whose purpose remained classified. They operated equipment without knowing what it produced. They solved individual problems without seeing the larger design. They were building the atomic bomb, but more than that, they were demonstrating something unprecedented, the industrialization of science itself. Germany had brilliant physicists. Werner Heisenberg understood quantum mechanics at levels that made him nearly mythical among scientists. German research into nuclear fission was sophisticated theoretical work of the highest order. In the 1,930 seconds, Germany led the world in atomic physics. But brilliant individuals pursuing theoretical understanding was not the same as organized systems pursuing practical application. The Manhattan Project was not about genius. It was about organization on a scale that defied comprehension. 30 sites across the United States and Canada. Entire cities built in secrecy. Oak Ridge, Tennessee appeared almost overnight. eventually housing 75,000 workers. Hanford, Washington sprawled across hundreds of square miles of engineered facilities. Each site performed specialized tasks: uranium enrichment, plutonium production, weapons design, metallurgy, chemistry, physics, engineering. Every scientific discipline coordinated toward a single objective. Germany had scientists working individually or in small groups, struggling for resources, competing for funding, operating without industrial infrastructure. When Heisenberg needed equipment, he requisitioned it through military channels that often had more pressing priorities. When he needed materials, he competed with weapons programs that offered more immediate returns. The Manhattan Project had essentially unlimited resources. Need a new facility, build it. Need rare materials, procure them. Need to test a theory, construct whatever equipment necessary. Money was irrelevant. Time was the only constraint. It was industrial research science conducted not in isolated laboratories, but across integrated networks of facilities, each feeding information to the others, each solving pieces of a larger puzzle. The plutonium production reactors at Hanford were marvels of engineering. Massive graphite structures cooled by Columbia River water operating at temperatures and radiation levels never before attempted. They produced plutonium gram by gram, building stockpiles through patient dangerous work that killed some workers and exposed others to radiation, whose long-term effects remained unknown. The electromagnetic separation facilities at Oak Ridge enriched uranium using processes that consumed more electricity than entire cities. Thousands of collutrons, massive devices using magnetic fields to separate isotopes, operated continuously. Each one produced tiny amounts of enriched uranium, but there were hundreds of them and tiny amounts accumulated into critical masses. Where Germany had vision, America had execution. Where German scientists sketched possibilities, American engineers built actualities. The difference was not intelligence, it was system, organization. The ability to coordinate vast resources toward objectives that might fail, that might prove impossible, that existed beyond current human capability. On the 16th of July, 1945, in the pre-dawn darkness of the New Mexico desert, the Trinity test proved the system worked. The explosion turned night into day, fused sand into glass, created a mushroom cloud that rose miles into the atmosphere. Watching from a bunker 10 miles away, scientists who'd spent years calculating, theorizing, and building saw their equations rendered into reality. Some quoted poetry, some stood silent. One physicist years later recalled simply thinking, "It worked." The whole impossible thing actually worked. This was not the triumph of one bomb, it was the triumph of organized thought, of industrial science, of a nation that could take theoretical physics and transform it into engineered reality through sheer systematic application of resources and intelligence. Germany had individuals. America had built a machine for creating machines, and the atomic age belonged to those who could systematize the impossible. They arrived as prisoners and consultants, as defeated experts brought to examine the machinery of their defeat. Operation Paperclip moved German scientists and engineers to America in the war's aftermath. Some willingly, some reluctantly, all of them carrying expectations shaped by years of believing in German technological supremacy. They expected to teach. They found themselves students. Wernher von Braun and his rocket team came from Peenemünde, where the V2 had been developed, the world's first long-range guided ballistic missile, a weapon that touched space itself. They'd achieved something extraordinary, something beyond what most nations even attempted. They arrived at American facilities prepared to explain their breakthrough, to share insights that would advance American rocketry by years. Then they saw what American engineers had already been developing. Research programs that paralleled and in some areas exceeded German work. Wind tunnels more sophisticated than anything in Germany. Testing facilities that operated at scales Peenemünde could never afford. Most striking, not individual projects starved for resources, but integrated programs with funding that seemed limitless. One German engineer remarked in disbelief, "We thought we were 10 years ahead, we were 10 years behind." Not in specific technologies. The V2 remained an achievement. German optics still impressed. Certain chemical processes showed sophisticated understanding, but in overall industrial scientific capability, in the systematic application of resources to technological problems, in the infrastructure that transformed theory into production, America had quietly pulled ahead, while Germany focused on individual brilliance. The laboratories surprised them most. Not primitive facilities needing German expertise to advance, but sophisticated research centers already pushing into jet propulsion, computing materials, science, nuclear physics, places where theoretical work transitioned smoothly into applied engineering, where questions about feasibility were answered by building prototypes and testing them, rather than endless calculation. At Wright Field in Ohio, German aeronautical engineers examined captured American aircraft alongside American examination of captured German planes. The Germans expected their designs to dominate the comparison: lighter airframes, more efficient engines, innovative solutions to complex problems. What they found instead was a different philosophy made manifest. American aircraft were heavier, simpler, designed for mass production and field maintenance. Less elegant in engineering terms, but there were thousands of them, and they'd won. The Americans examined German designs with professional interest, admiring certain solutions, noting innovative approaches, occasionally adopting ideas that offered improvements. But there was no awe, no sense that German engineering represented an insurmountable lead, just colleagues examining alternative approaches to shared problems. It was humbling in ways combat never achieved. Combat could be explained by resources, by numbers, by circumstances. But standing in American research facilities, seeing the depth and breadth of ongoing work, understanding the systematic nature of American technological development that revealed a truth more profound than any battlefield defeat. Germany had worshipped individual genius, the brilliant scientist, the visionary engineer, the master craftsman whose skill exceeded all peers. It was a romantic vision of technology, where great men produced great things through force of intellect and will. America had built systems. Research laboratories connected to universities, connected to industrial facilities, connected to military requirements. Information flowed between them. Problems identified in combat reached engineers within weeks. Solutions developed in laboratories reached production within months. It wasn't romantic. It wasn't about genius. It was about organization, process, the systematic conversion of knowledge into capability. The German scientists' surrender became collaboration.
Indeed.
Their pride, confronted with this reality, transformed slowly into respect. Some resisted, insisting German approaches remained superior despite evidence otherwise. But most adapted, recognizing that they'd joined not a defeated nation requiring their expertise, but a technological infrastructure that had simply evolved along different principles. The two worlds merged, a German expertise in specific areas combined with American systematic application. And from that synthesis, the post-war technological explosion accelerated further. Genius and system finally united. The war's greatest lesson was not the bomb or the tank, or any single weapon that littered battlefields from the Pacific to Berlin. It was the system that built them, the realization that technology had fundamentally changed from the product of individual genius into something larger, something organizational. For centuries, advancement came from brilliant minds working in isolation: Archimedes, Leonardo, Newton, individuals whose intellect pushed humanity forward through sheer force of thought. The Second World War proved that era had ended. Technology was now the product of coordination, of resources marshaled systematically, of problems broken into pieces and distributed across thousands of workers, each solving fragments that combined into solutions no individual could conceive alone. The Germans had worshipped the engineer, the singular mind that could envision perfection and build it through skill and determination. The Americans had empowered the factory, the system that could transform adequate designs into overwhelming quantity. In the end, it was not who had the smartest men that determined victory. It was who had the smartest machines, who had the infrastructure to turn intelligence into production, who understood that modern war, modern everything, would belong to those who could organize knowledge itself into industrial output. The age of the individual genius had passed. The age of systematic innovation had arrived. Dawn breaks over Detroit. The night shift ends. Workers stream from factory gates, faces smudged with grease and exhaustion, carrying lunch pails emptied hours ago. Behind them, the machines cool. Steam rises from vents. The thunder that shook the earth for 4 years finally begins to quiet. War revealed not just destruction, but creation on an unimaginable scale. The capacity to build, to produce, to organize human effort into outcomes that reshaped the world itself. For the men who once believed they led the world in technology, it was humbling. Not the humiliation of defeat in battle, but the deeper recognition that they'd misunderstood what technology had become. For America, it was transformation. From a nation of tinkerers and inventors of individual workshops and clever mechanisms into the architects of modern industrial power, they thought victory would come from genius. Superior minds producing superior weapons through superior skill. But in the end, victory came from the machine. The factory hum fades into silence. The war is over. The future has already begun.